Yes, but I need this pencil all day, so I cannot get the pen out with this pencil.
Huh. Okay. Background. Here's a little bit of background you're going to need. If this is something you ought to be able to do. If you're given two rational expressions and are asked to add them together, after that cornerback there shuts their mouth, we are going to get a seating chart when term 3 starts. Oh yeah. Because I just get tired of saying, shh, shh, hey, be quiet, come on, let's get going, hey, we got to get going. I get really tired of that. So a seating chart, I think, will be a great remedy.
But I think you're hallucinating. I think you need to give a different class.
Oh, it's this one. It's probably one of my noisiest classes. So how would we add these together? Common denominator. This is something we learned in our first unit. So this expression becomes 2x minus 4 over your common denominator, x minus 2, x plus 1. Then we're going to add 3x plus 3 over the common denominator. Now that we have a common denominator, we add the numerators to give 5x minus 1 over x minus 2 times x plus 1. Now let's take a step back and look at what we've done. We started with two separate rational expressions. We combined them into a single rational expression. Would you guys agree with that? Hey, Savvy, what's up? Did things get worked out? That's right, thank you. So, come on, you guys. We took two rational expressions and combined it into a single. Would you guys agree with that? Partial fraction decomposition is going the other way. You're going to be given a rational expression like this, and by the we haven't learned the process yet, but doing the process of partial fraction decomposition, we're going to take this and write it as those two separate. These are called the partial fractions of this rational expression. Does that make sense? What's the reason for it? Next year in calculus, you may or may not have heard of this. Have you heard of integration? By taking the integral, it's much, much easier to take the integral of two partial fractions than the integral of a single rational expression. It's much easier. Okay? So next year in calculus, you're going to be given something like this. You're going to be asked to find the integral. You're going to have to decompose it into partial fractions before you find the integral. Okay? And really, that's the only time you're going to use this, pretty much. Yep. Yep. So let's get into it. This is objective 1. The form of partial fractions. The thing that makes these tricky, the arithmetic and the steps involved really aren't that hard, but there's just different ways to do it depending on what the original expression looks like. Okay. So we're going to start with, I'm going to call these cases. Case 1. So given some rational expression, let's call it P of x over Q of x. And here's what differentiates the different cases. Case 1, case 2. There's 3 of them. Case 1, case 2, and case 3. There's actually 4, but I'm going to skip the 4th one because you never, ever, ever see the 4th case.
What if we do?
You won't.
What if we do?
Then I'm sorry. But anyway, and it's the denominator that differentiates between the different cases. So Q of x is the product. What does product mean?
multiplying, it doesn't have to be necessarily 2, but you're right, it's multiplying a number of factors together. Q of x is the product of, well, I'm going to use some big words here, distinct linear factors. So if your denominator is the product of distinct linear factors, then you are in case 1, and there's a particular way that you have to write the form of the partial fraction. Okay. Then your original expression, P of x over Q of x, is decomposed in the following fashion. A You guys are all decomposing right now, aren't you?
Yes, but doesn't decomposing usually make something smaller? No.
It is. It is technically breaking it up into smaller pieces. What's that? Don't think about it as the number of terms. Think about it as the degree of the numerator compared to the denominator. If you take a look at what we have here, this is a degree 1 divided by a degree 2, right? But if you break it up into its partial fractions, this is a degree 0 divided by a degree 1. This is degree 0 divided by degree 1. So even though it's more pieces, they're more simple pieces, I guess you could say. Let's talk about this right here. Okay? A, B, and A sub n, these are just constants. A, B, C, D, these are just going to be constants in the numerator. Your denominator are the factors of Q of x. Okay? So depending on how many factors of Q of x there are, that's how many pieces of the partial fraction you're going to have. For example, you guys can understand this. Okay? If you have a quadratic, let's say that Q of x is quadratic, something like x squared plus 7x plus 10. How many factors are there in a quadratic? If you factor a quadratic, how many factors do you have? 2, right? So if Q of x was quadratic, you're going to have 2 factors. How many pieces of the partial fraction would you then have? Just 2. Okay? And this a1x plus b1 and a2x plus b2, those are just your factors of the quadratic. You can have an a and a b. Okay? So let's just do a concrete example. Here's what makes more sense. Example 1. Let's say that our rational expression is something like 5x plus 6 over x squared minus x minus 12. This is example 1. And I want you to write the form of the partial fraction. The difference between objective 1 and objective 2, which we haven't got to yet, objective 1 is just to write the form of the partial fraction, but we don't know what A, B, and C are yet if we just write the form. Objective 2 is then to find out what A, B, and C and all the other pieces equal. First thing we got to figure out is Q of x, our denominator. Okay? Is Q of x the product of distinct linear factors? Well, right now, Q of x isn't the product of anything. It's the sum of just a bunch of terms, x squared minus x minus 12. That's not the product of anything. So how do we write Q of x as the product of factors? We have to factor it. Good. So first step is to factor Q of x. So we have 5x plus 6. Parker, say that again.
X minus 4 times x plus 4.
Thank you. Not bad for a BYU fan. Just kidding.
Shall we go to the test score?
No. No, let's not go there. Now, you guys, yes or no, listen carefully. Does this expression right here fit this description? Q of x is the product of distinct linear factors. Does it? Are these factors linear?
What does it mean to be linear?
Straight line.
If you were to graph them, they'd be a straight line, okay? Are they distinct? What does the word distinct mean? Different?
They are.
They're all thing. There's only one x minus 4, and there's only one x plus 3, so they're distinct. So they are distinct linear factors. That means this expression can be decomposed using this model right here. Okay?
So the form of the partial fraction is going to be a over one of the factors, and it doesn't matter which order you go in, just choose one of the factors. I'm going to put x minus 4 first, and then plus b over x minus or x plus 3. This is what's called the form of the partial fraction. What we're going to do here in a couple of minutes is learn how to find the actual values of a and b. Right now, if all the directions say to write the form of the partial fraction, that's where you stop. Okay? If the directions say to find the partial fractions, then you'd have to find the values of a and b. But they just want you to write the form of the partial fraction.
Does it matter
Okay.
which goes underneath which?
Nope. Nope. Let's try another one.
Are you going to use these for part 2? Are we going to use these for part 1?
Yeah, we're going to, well, maybe not these exact ones, but ones like them. We're going to have to go back and find the values of a and b. So example 2, 3x plus 1 over x minus 1 times x squared minus 4. Same directions, write the form of the partial fractions. First thing we got to do is consider q of x in its fully factored form. Right now it's partially factored. It's the product of two factors, but
One of the factors isn't fully factored. X squared minus 4 can be reduced
to two more factors. It's the difference of squares. Exactly. So it's going to be 3x plus 1 over x minus 1, x minus 2, x plus 2. You always need to check,
Are these distinct and are they linear? Are they the product of distinct linear factors? They're all linear and they're all distinct.
this time there's three of them though. There's three factors. So how many pieces do we need in the partial fractions? 3. So we're going to have a over something plus b over something plus c. What's the denominator going to be?
Yeah. Just each factor, and again, it doesn't matter what order they go in.
You can put them in any order. A over x minus 1 plus b over x minus 2 plus c over x plus 2. Okay? That's case 1. Let's do case 2. P of x over q of x. And this time q of x is the product of linear factors, some of which may be repeated. So the difference between case 1 and case 2, not all of the factors are distinct. You may have factors that are repeated. So there's a slightly different way that you have to set up the partial fractions if there are factors that are repeated. So here's the form of the partial fractions. P of x over q of x is equal to a over ax plus b plus b over ax plus b quantity squared plus a sub n over ax plus b to the nth power. Where n is the number of times that that particular factor repeats itself. For example, if you have one factor that repeats itself 3 times, okay, how many pieces are you going to have? If you have a factor that repeats itself 3 times,
You're going to have 3 pieces. You're going to start with a normal piece, ax plus b, then that factor to the second power, and then you're going to end it with that factor raised to the third power.
okay? So let's do an example here. Example 3. Example 3.
I need one example.
X plus 4 over x plus 1 times x squared plus 2x plus 1. First thing we got to do is factor q of x.
We're in the top, the x plus 4.
X plus 4, yeah. Because both case 1 and case 2 deal with factors that are linear. Right now we have a linear factor and a quadratic factor. So as it is, this wouldn't be case 1 or case 2 because not all the factors are linear. So we got to factor this one. How does x squared plus 2x plus 1? X plus 1 times x plus 1. So we're going to have x plus 1, and another x plus 1. So this is the product of linear factors, but they're not distinct. This is the same linear factor repeated 3 times. Okay, so the form of this partial fraction, we're going to have 3 pieces because it repeats itself 3 times. But the difference between case 1 and case 2 is how you represent the partial fractions. Okay? Because this is a repeated linear factor, each time you write it in the denominator, you have to increase the power. So x plus 1 to the first power is the first piece, and then you're going to have x plus 1 to the second power, and then you're going to have x plus 1 to the third power. And we stop at the third power because it repeats itself 3 times.
Had this only repeated itself twice, for example, if we got rid of, let's say I got rid of this first x plus 1 factor right here, so we only have 2 of them. What difference would that have made? You only have the a and b, and you wouldn't need this third term here. Does that make sense? Most of the time, though, you're going to have a combination of case 1 and case 2. You might have some that are distinct, some that are repeated.
We'll take a look right now. Let's do example 4. Write the form. Yeah. This is the short one. Yeah, but that's not case 1 or case 2, that's case 3. Clocks are broken, you guys,
All around the school they are.
in every classroom.
Really?
Don't know what happened.
They're all at the same time.
It's too much jerks. First kind of bounces, like goes down.
Yeah. In Spanish, it's stopped at the exact same time.
Like
Maybe
the
we'll
New
fix
Year's.
it so that it stops 2 minutes ahead of every New Year just tells them they freeze.
Anywho, x squared plus 7x plus 12. Come on, help me out. X plus 4. X plus 3. So we have a combination of two of things happening here. We have
Two factors that are distinct, x minus 3 and x plus 4, but then we have a factor, x plus 3 that's repeated.
so, and it doesn't have to necessarily be done in this order, but you're going to have to follow case 1 guideline and case 2 guideline. Case 1 guideline, if we're talking about the x minus 3 and the x plus 4, if those were the only two factors that we're dealing with, that would be a over x minus 3 plus b over x plus 4. So those are the partial fractions for the distinct linear factors.
Would that be C?
Exactly. Now we've got to do,
3 and D over x plus 3 squared?
yep, now we've got to do our partial fractions for the repeated linear factors, which is x plus 3, x plus 3. So since we already have an a and a b, we need to use a c. So it's going to be c over x plus 3 plus d over x plus 3 squared. And those are the partial fractions. Case 3. Given p of x over q of x and q of x is an irreducible quadratic factor or it could be the product of irreducible quadratic factors. It doesn't just have to be one. Let me actually rephrase that. Q of x is the product of irreducible quadratic factors. What does it mean to be irreducible quadratic factors? You can't simplify it. Yeah, keep going. If it's irreducible, it doesn't reduce if it doesn't factor. Okay? Irreducible quadratic factors do not factor. Then p of x over q of x is decomposed in the following way. Ax plus b over a1 x squared plus b1x plus c1 plus, and I'm just going to leave the dot 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 because it just depends on how many irreducible quadratic factors there are. If there's 2 irreducible quadratic factors, you're going to have 2 pieces. Okay? If there's 3 irreducible quadratic factors, you'd have 3 pieces. For example, most of the time, you're going to see this case 3 in combination with case 1 or case 2. So that's what we're going to see here. Let's do 5x squared plus 1 over x squared minus 1 over x squared, or times x squared plus 7x plus 2.
So we have two quadratic factors here. One of them is reducible, one of them is not. X squared minus 1 can simplify.
It can factor. This is an x squared plus 7x plus 2. So this one is not factorable. But let's at least write it with the one that factors. So let's first deal with the two linear factors. We have x minus 1 and x plus 1. What would the partial fractions of those look like? A over x minus 1 plus b over x plus 1. Now we need to... How many more pieces do we need?
Just one more piece, because all we have is one more irreducible quadratic factor. The difference here in case 3 is the numerator. Take a look at the numerator in your form of the partial fraction. The numerator is no longer just a constant a and b. You see, the numerator is now a linear expression. And if we've already used a and b,
CX.
So it's going to be cx plus d. Over your irreducible quadratic factor of x squared plus 7x plus 2.
Wait, why does it say CX?
Because we've already used a and b.
Oh, okay.
Now, the case that we're skipping for a couple of reasons, you very rarely see it and we just don't have time for it. You could probably guess. Case 4 would have been what?
The double.
Repeated irreducible quadratic factors. So if I had put an exponent of 3 right here, for example, this would be a repeated irreducible quadratic factor, right? What would that have done to this?
Then it's like that, it's squared.
you'd have to have more of those pieces, one of them squared, one of them cubed. Those are
Horrendous. And you very rarely see them. Anyway,
Wait, it's around this time in partial?
no, it's to find the A, B, C, and D and all the values. Let's go to objective 2. We've written the form of the partial fractions. We need to actually find the partial fraction. Now find the partial fractions. Ooh, this is where it gets fun. I'm excited for this. I am. It's none of the above.
I can handle part. Is it long?
Not really, no.
I can handle part. Like the row thing where you had like took like 15 minutes to do one problem.
For what?
The one where you like transpose the matrix.
The inverse of a matrix. Okay. Find the partial fractions of this expression 12 over x squared minus 9. The process is to first decide what case this is. Is this an irreducible quadratic factor? Is it a quadratic factor that can be reduced to distinct linear factors or repeated linear factors? Because you first have to set up the form of the partial fraction. So what are we dealing with here? Case 1, distinct linear factors. So this is 12 over x minus 3 times x plus 3. Let's keep track of some steps here. Steps. Step 1 is to write the form of the partial fractions. That's what we just practiced for the last half hour. So the form is going to be a over x minus 3 plus b over x plus 3. That's step 1. Step 2. Is to multiply both sides by the LCD. This is an important step, because right now we have an equation that's rational. It has fractions, it has denominators involving variables. If we multiply both sides by the LCD, we're going to end up with an equation that has no fractions at all. Would you rather solve an equation with fractions or without? Without. That's why step 2 is so critical. It's not absolutely necessary maybe, but it's critical to make this a much easier equation to solve. I guess if you can find the LCD, but it's not really that hard. What's the LCD? Lowest common denominator. Which one is it? That's part of it. What is the LCD, guys? Come on. Yeah, it is x squared minus I. If this entire expression right here were to have the same denominators across the board, what would that denominator be? X plus 3, x minus 3. Okay, that's the LCD. Okay, just by the way, the denominator you start with is always going to be the LCD. Always. Okay. But anyway, if we multiply both sides by that LCD, x minus 3 times x plus 3, we're going to multiply it over here, and then we multiply over here x minus 3 times x plus 3. What do we end up with on the left side of the equation? Come on, easy question. On this side right here. Yeah. You just end up with 12. On the left side of the equation, the denominator cancels out completely with the LCD because the LCD was that entire denominator. On the right side, you have to take your LCD and multiply each piece separately. For example, if we take this entire LCD and multiply just that piece right there, what happens? This is easier than you guys think. I think you're making it to be much harder than it is. When do the x minus 3's cancel? So it's just a times x plus 3. Okay? Now, if the LCD multiplies to that term with the b, then this time the x plus 3's would cancel, so it's b times x minus 3. So, these two expressions are the same. The one we started with and the one that we have now, they're equivalent expressions, but which one looks easier? The one we started with or the one we have now? This one looks easier. We cleared the fractions by multiplying both sides by the LCD. Okay? Usually in an equation involving x, isn't that what you solve for, x? We're not solving for x though. What is it we're solving for here? We're solving for a and b. We're not solving for x. Okay? So, I'm actually not even going to show you the first way. I'm just going to show you the second way. We don't have time. Yes. Step 3 is to choose what I like to call convenient values for x. Since we're not solving for x, we can let x equal whatever we want. Because it doesn't matter what x equals. We don't care what x equals. We're trying to find the values of a and b. Okay? So we need to choose convenient values for x. And what I mean by convenient values, if we have one equation with two unknowns, a and b, can we solve one equation with two unknowns? No.
So what we need to do is choose values for x that gets rid of one of the unknowns. For example, if I let x equal 3,
It's gonna be
what happens to b? It disappears. Now what do we have left to solve for? 8. Okay? So one of the convenient values we're going to choose is x equals 3, because that's going to make b disappear. But there's one more convenient value we have to choose. What would make a disappear? Negative 3. So those are the two convenient values of x we're going to choose, because those make each term disappear. Okay? What's that? A yellow sticker? Weird. Thank you. That's embarrassing. So for this problem, we're going to let x equal 3 and x equal negative 3. So if x equals 3, then the equation becomes 12 equals a times 3 plus 3 plus b times 3 minus 3, which becomes 12 equals a times 6 plus what? Plus 0. So then a equals 2. Okay. Now we do the same thing for the other convenient value of x. If x equals negative 3, let's solve the equation again. Then we're going to have 12 is equal to a times negative 3 plus 3 plus b times negative 3 minus 3. So this term involving the a disappears because it becomes 0. B multiplies negative 6. So what's the value of b? B equals negative 2. We have the value of a and we have the value of b. Those were the two things we needed to solve for. Okay? So now we finished the partial fractions. We knew the partial fractions were a over, what was it, x minus 3? A over x minus 3 plus b over x plus 3. We knew what the partial fractions looked like. We just didn't know the values of a and b, but now we do. So to finish the problem, you write this as 2. Actually, b is negative 2, sorry. 2 over x minus 3 plus negative 2 over x plus 3. And those are the partial fractions right there. Now, how would we check this? We've done a lot of steps. The potential for making small mistakes is huge. How would you check your answer? If we were to add these two together into one expression, what would that one expression be? 12 over x squared minus 9. And it would be. If we were to add these two together, then you get 12 over x squared minus 9. Okay? This is how it works.
This is not the way the book would show you. That method takes a lot longer.
Yeah, I like this method.
This way is much faster. Let's do another example. There's a few. Okay. Let's do this one. 2x plus 1 over x squared plus x minus 2. First thing we got to do is, if possible, I guess, we've got to write the denominator in terms of its linear factors. X squared plus x minus 2 What is it? X plus 2. X minus 1. So now we write the form of the partial fraction. This is still a case 1 because they're distinct linear factors. A over x plus 2 plus b over x minus 1. All right, let's go through it. We got to speed this up because we have 3 more examples to do. What's the first step? Well, I guess that was the first step. What's the second step? Multiply both sides by the LCD. Really, all you need to concern yourself with is the right side, because on the left side, what's always going to happen on the left side? All you're going to have is a numerator. The denominator is going to cancel out every time. Okay? So this equation becomes 2x plus 1 equals a times x minus 1 plus b times x plus 2. So the convenient values, we're going to let x, say that again, Trent. X equals 1 and x equals negative 2. Good. So if x equals 1, the equation becomes 2 times 1 plus 1 equals a times 1 minus 1 plus b times 1 plus 2. The left side is 3. The right side becomes b times 3. So b has to equal 1. Now if we let x equal negative 2, now the equation becomes 2 times negative 2 plus 1 equals a times negative 2 minus 1 plus b times negative 2 plus 2. The left side is negative 3. The right side is a times negative 3. So a also equals 1. So the original partial fractions that we had were a over x plus 2 plus b over x minus 1. We can now write that as 1 over x plus 2 plus 1 over x minus 1. Okay. What example are we on? 28? Example 8? Woo! Because it's winter time?
No, why is it supposed to be blue?
Because it's a math.
I'm trying to save energy.
Uh-huh.
Costs a lot of money to heat a room this size, and then times that by however many rooms are in this building, 60, 70 rooms. It's a lot of money. Somebody does. The taxpayers do, so indirectly I do pay for the heating. You guys don't pay taxes, you don't care. I pay taxes, so I'm trying to conserve energy.
You're gonna have to pay for it anyway. Might as well use it. No. All right, this one's gonna be a little tricky. We'll end on this one. We don't have to factor anything because it's already factored. For some reason, I don't know why this happens, because it's really not that hard. This piece right here confuses the heck out of some students. Is it a linear factor? Is it repeated? What the heck is it? It's x plus 0, yeah. So it's a distinct linear factor. Okay? So we have to form a partial fraction just for that piece. What's the partial fraction for that piece going to be? A over x. Good. And now we have to have the partial fractions for this repeated linear factor. So we're going to have a b over x minus 1 plus c over x minus 1 squared plus d over x minus 1 cubed. Ooh, man. Can anybody see a potential problem here? We say that again? What's not going to cancel out? But when we multiply both sides by the LCD? Okay. Let's take a look at that. What is the LCD, by the way? It's this whole entire thing. It's not just x times x minus 1. It's x times x minus 1 cubed. So if we multiply this entire side by x times x minus 1 cubed, the left side, all we're going to have is x squared plus 1. That's not so bad. We've got to be really careful on what we decide cancels and what we decide doesn't cancel. When that LCD multiplies all the way over here to the first term, what cancels? The x cancels. So it's going to be a times what? A times x minus 1 cubed. Okay, good. Now watch very carefully. When this LCD multiplies the b term, the x minus 1 is going to cancel with one of these x minus 1s. So it's going to be b times x minus 1 squared. Good. Now when the LCD multiplies the c term, it's going to be c times x.
So you're basically just flipping the denominator. You're just carrying on a with the denominator.
In a way, yeah. In a way, yep. And then, what about that last term, d? Just becomes x. Can anybody see another problem? The convenient values. What are the only two really convenient values we're going to choose here? 1 and 0, but the problem is we have 4 terms, but only 2 convenient values. Okay?
Well,
We're going to have to choose convenient values that may not be so convenient. Let's let x equal 0 and x equal 1. Yeah.
So you can only have 2.
No, you can choose as many values as you want for x. The ones that are probably most obvious would be x equals 0 and x equals 1. Let's just decide on what's going to happen here. If x does equal 0, what cancels? Just b? Everything but a, right? Because if this b, right, if this x is 0, then doesn't the b term cancel?
And if this x is 0, doesn't the c term cancel? So if we at least let x equal 0, we can find a.
A is 1.
Okay? Now, what about x equals 1? If x equals 1, what's going to cancel? The a is going to cancel. The b is going to cancel. And the c is going to cancel. So if x equals 1, what can we find? D. But what haven't we found after that? We haven't found b and c.
Let's at least find a and d, though. If x equals 0, then we're going to have the equation 0 squared plus 1. Now, to save time, the b and the c and the t term and the d term are going to cancel. So we're just going to have a times 0 minus 1 to the third power. Everything else is going to be 0. So we're going to have 1 is equal to a times, be careful here, negative 1 cubed, which is negative 1. So then a equals negative 1. Now, if x is equal to positive 1, then the equation becomes 1 squared plus 1, which is 2. So 2 equals... What did we decide would cancel if x equals 1?
Everything but the a term, the b term, and the c term are gone. So I'm not going to write them. It's going to take too long.
What we would have left is 2 is equal to d times 1. Try that other way.
I mean, you know what?
D equals 2. Yeah. Okay. We've chosen convenient values that cancel terms. What we're going to have to do now is just choose random values for x. They're not going to cancel terms. Okay? So, other than negative 1 and positive 2, what's another nice value for x? Actually, 0. Sorry, these were the values we chose. X equals 0 and x equals 1. What else would be a nice value of x we could choose? Let's choose negative 1. Okay? Let x equal negative 1. But we also know two other things.
We also know a and b. Do you guys agree? So we're not only going to let x equal negative 1, we're also going to let a equal negative 1 and d equal 2. Because that's going to reduce the amount of unknowns in our equation.
So we're going to let x equal negative 1, we're going to let a equal negative 1, and we're going to let d equal 2. Now we're going to solve the equation again. So if x equals negative 1, the equation becomes negative 1 squared plus 1 equals... Yeah, we're out of time. Poof. The bell's going to ring in about 30 seconds. We'll have to pick this up next time.